Hi there, Parker Glynn-Adey here with Math 223. We're going to look at the solutions to activity number 3, the true-false questions from week 11. Okay, so we're going to start off. If A is a 3 by 5 matrix and rank of A is 2, then the dimension of the null space of A is 3. Okay, so what we need to understand is what exactly do we mean when we say a 3 by 5 matrix? I just want to put a little note off to the side to remind myself that n by k matrices have n rows and k columns. Okay, just a little bit of a reminder. So is it possible to have rank A be 2 and the dimension of the null space be 3? So let's look at an example of a matrix with rank A equals 2. Right, so we start off with a leading 1. Another leading 1. Okay, so here we have rank 2. And here we have null space 3. Okay, so this strongly suggests that this works. Okay, this is an example of it. We can also check that this satisfies the rank nullity theorem. Right, so the dimension of the image of A plus the dimension of the null space of A has to add up to the number of columns. Right, so here we've got 2 plus dimension null A is 5. And we can do a little bit of arithmetic and get that the dimension of the null space has to be 3. Okay, so this is totally generally true according to the rank nullity theorem. Nice. Okay, so let's move on. We'll look at our next true-false question. Okay, now we've got the same kind of thing. Let's look at this abstractly. So we'll say the dimension of the image of A plus the dimension of the null space of A has to add up to 6. So that tells us dimension of the image of A plus 2 has to be equal to 6. So this tells us that we have to have a 4-dimensional image. Okay, so this is false. The answer to question 2 is false. We cannot have the dimension being equal to 2. Okay, let's move on to our next true or false question. If we have a 3 by 3 matrix such that this has no non-trivial solutions, then the columns form a basis for R3. Okay, so this is bringing in several ideas related to matrices, related to column spaces, related to images. So I just want to recall what's going on there. That the dimension, or recall just that the dimension of the image is the span of the columns. Okay, so the image is the span of the columns. So the dimension of the image of A is going to be the dimension of the span of the columns. Okay, now what we want to do is we want to relate this back to non-trivial solutions of this homogeneous system. So what can we do there? Right, so if AX equals 0 has no non-trivial solutions, then its null space has just a single vector in it, right? Its null space is only the trivial set, right? Trivial vector. So what that means is that the null space is zero-dimensional. Okay, so let's put that together with the rank nullity theorem and see what that tells us about the image. Right, so the dimension of the image plus the dimension of the nullity has to be this number of columns here. Right, so we have to add up to 3. So putting that together with what we know, that it follows that the dimension of the image must be 3. So what that's saying is that the dimension of the span of the columns is 3. And that implies that the columns of A span all of R3. Okay, and if we span all of R3, then we're a basis for R3. Okay, in this instance, what we have is true. We have that the columns form a basis for R3. Okay, kind of a neat thing. If you're an invertible matrix, your columns span all of space. If there's anything that you'd like clarified here, please feel free to ask on Piazza. All right, so we're going to move on to the next true-false question. If U is null A, then the only basis is the set of basic solutions. Aha. So when I'm faced with something like this, I like to come up with an example just to kind of convince myself of what's going on, to have a look at what's happening. So I'm going to just take a moment and experiment here. I'm going to see what's up with this really negative matrix, right? Or really zero matrix, right? That's going to give me that AV is 0 for any V, right? So its null space is going to be the whole plane. And now when I think about the whole plane, I say to myself, wow, the whole plane has a lot of basis vectors, right? I could start off with the standard basis vectors. Right, I could think about E1 and E2, but we saw that any pair of non-parallel vectors is going to span the plane, right? So I could also take, V and W, right? These are non-parallel vectors. They'll span the whole plane. So we're going to get that this null space can either be written as the span of E1 or E2, and it'll also be the span of any non-parallel vectors V and W. Okay, so this suggests that we have a lot of freedom in choosing these basis vectors. So I would say that this question is false, right? There are many, many sets that span this null space. Okay, so this, if you work through the algebra here, this first set that we wrote down is the set of basic solutions. But we've got a lot of freedom to choose different bases for this set. So I would say that this question is false. Okay. If you want to come up with some examples or you want to discuss this, please ask on Piazza. Okay. Let this be two non-parallel vectors. If U is the plane through the origin, then this is a basis for is a basis of U. Okay, so we want to say, can every vector in that plane be spanned by these two guys? So our picture something like this. We have the origin here. We have V. We have W. And now we're saying these are non-parallel vectors. We're spanning this plane, and we'll say that this is a basis. And that's true, right? This is a basis. Because U is defined to be the span of those two vectors. Right, so every element in that span can be written as a linear combination of those two guys. Okay, sometimes it's helpful to kind of explore around a question to kind of build some understanding of what's going on. I want to just to kind of make a fine point of this, to explore what would happen if we had three vectors. So to just vary the question a little bit and say, let U, V, and W be three non-parallel vectors. if U plane spanned by UVW, then UVW is a basis of U. Okay, so just to kind of vary it, to add a couple more vectors here, here the answer to this question would be false, right? Because the dimension of that span is 2. And in order to be a basis, we need to have dimension 3. Okay, so here we don't have the same dimension, or this is a non-minimal set. Another way to say this is there are vectors on the plane there are going to be vectors in the plane which can be written non-uniquely using U, V, and W. Oops, sorry. The dimension of this span should be the dimension of the span of those 3 vectors, pardon me, U, V, and W is 2. To be a basis, we need the dimension to be 3. In any case, they're going to be vectors which can be written non-uniquely using these, so these guys can't be a basis. Okay, so for this original question, the answer is true. And for this alternate question, the answer is false. Okay, very good. So let's move on to the next question from the activity. If UV is a basis for U, then U plus V, U minus V is a basis. Aha, okay. So what we need to do here is we need to check that that these guys span the same object. Okay, so the first thing that I want to note is that these guys, U can be written in terms of these 2 vectors, and V can also be written in terms of these 2 vectors. Okay, so what that's telling us is that U is in the span of those 2. Okay, and obviously we have that the reverse is also true. Okay, so what we've obtained is that these 2 sets span the exact same space. Right, so these will define exactly the same plane. Okay, so I would say that this is true or correct. Okay, so they define the same exact subspace. Very good. Now let's move on to activity 7. Right. This is very sneakily related to the previous activity. Okay, so notice that if we take E1 in the following way, right, then we get that E1 plus E2 is 1, 1. And E1 minus E2 is negative 1, 1. So these are very similar. What we're doing here is we're saying, okay, trying this out on a particular pair of vectors. I think it's insightful to look at this geometrically as well. Right? If we look at those two vectors, 1, 1, and 1, negative 1, then we see that those guys are non-parallel. And if we're non-parallel and non-zero, then we span the whole plane. Okay, so this is a basis of R2. Okay, so the answer to this question is true. Okay, now moving on. Right, this is sort of the reverse of this question. Right, there's a relationship there, and here we can get away by noting that just as before, that these span the exact same space. Right, we have that these are the exact same span. Okay, so these 3 questions I think will help you get your notions about spans and bases, right? Because all 3 of these are pretty intimately related questions. Okay, so thank you very much. If you've got any questions about these solutions, please ask on Piazza, and one of the instructors will be happy to help you.